Welcome to chapters 1 and 2. In this chapter, we are going to talk about groups, and groups is the first big topic in abstract algebra, in our abstract algebra course. We will be talking about this for weeks and weeks. So, what's a group? Well, a group really, the way I want you to think about it to begin with, is think about a set of stuff. So, our group right here is a set of stuff. Set of elements together with some kind of way to combine elements. So let me just say a way to combine elements. And then there are a few other things, plus some other stuff that has to be true about what happens in a group. But really, you have a set of elements, a set of stuff, and we define a way to take two of those elements, combine them to get another element in our group. And this way of combining elements, we call that a binary operation. So that is the first thing that we want to define. What do we mean by combining elements? So let's read the definition. Let G be a set, then a binary operation or just operation on G is a function that assigns to each ordered pair of elements of G an element of G. Okay. Often it's the case, let's look at examples right away just to be able to visualize what's going on here. So our very first example is one that's very familiar to us, and that is addition is a binary operation on the set of integers. So Z is a set of integers, and addition is a binary operation. So you take two integers, let's say 3 and 4, and we can add them, and out comes 7. That's again an integer. So both 3 and 4 are integers, and so is 7. So all of those are integers. And addition is our binary operation that we're using to combine those elements in our set of integers. Another example that you've also been using a lot is matrix multiplication. So matrix multiplication is a binary operation on the set of all 2 by 2 real matrices. It's also a binary operation on the set of 3 by 3, 4 by 4, 5 by 5 real matrices. But let's just look at the set of 2 by 2 real matrices. Then if we are taking one of those, so let's say 1, 2, I'm just picking one at pretty much random right here. So here is one matrix, and then I multiply another matrix to the first one, and using our normal rules for matrix multiplication, so 1 times 1 plus 2 times 0, that is 1. And then the first row second entry is first row in the first matrix times second column in the second matrix. So that's 1 times minus 1 plus 2 times 1. That is also 1. And we get minus 1 and we get 4. So this is just our normal matrix multiplication. But you can see we started with 2 by 2 matrices, and we got out another 2 by 2 matrix. So matrix multiplication is a binary operation on the set of all 2 by 2 real matrices. Now, those are two examples of binary operations. Let's look at an example of something that's not an example. That's also usually very enlightening. So division is not a binary operation on Z. And why is that? We can certainly take two integers, so 3 and 4 again. Let's take 3 and 4 just as we did before and divide 3 by 4. The outcome is 3/4. We can do that, but 3/4 is not an integer. It's not in our set Z, even though 3 and 4 both are, so they are in Z. But 3/4 is not in Z, and so that breaks our rule for something being a binary operation. So the outcome has to be, again, in the set that we started with. Okay, so now that we know what a binary operation is, let's look at the definition of a group. So let G be a non-empty set together with a binary operation that assigns to each ordered pair AB of G an element of G, denoted by AB. So this is the combination of our two elements. So A and B are our two elements in the set G that we are starting with, and then we are combining them, adding them, multiplying them, depending on what our binary operation is, and the outcome of that operation is denoted by just AB written next to each other. We say that G is a group under this operation if three things are true. And that is, the first that has to be true is that if you combine A and B and then take the outcome and combine it with C, so that's what's happening on the left here, is the same as if you first had combined B and C and then taken the outcome of that and combine it with A. So this has actually a name. This is the associative property. And it's certainly true for the integers in Z. So just to give another example, if you have 3 plus 4 and then you add 2 to it, that is the same as if we had first taken 4, added 2, and then added 3 to it. So that is the associative property, number one. The second thing that has to be true about a group is there exists an identity element. We are going to denote it with a small letter E. So there exists an E in our group G such that when you take any element in your group and you multiply it or you combine it with E, either from the left or from the right, it doesn't do anything. It just returns the element itself. So that's the identity element. So in the integers, so if we are looking again at our example of integers, it would be the number 0. 0 plus 2 is the same as 2 plus 0, and that is true for anything, not just for 2. So that's an example. Number 3, for each element in G, there exists another element in G that we're going to call the inverse of A. So there exists this element B, such that when you are combining A with B, either from the right or from the left, you get the identity element. So that is our definition of an inverse. And you have to be able to find an inverse for every single element in our group. Now, 2 notes. The first one is the inverse of A is often denoted by A to the minus 1. And be careful right here. So it's the notation for our inverse. A inverse is not the same as 1 over A. I know we are used to that in the set of real numbers. We are using exponents this way, but in this class, this is not going to be the case. In abstract algebra, A inverse really just denotes the inverse. And in the set of real numbers, it coincides with our idea of division, but in general, it has nothing to do with division. Now, the second note, a group is called abelian if it has an additional property. If it has a property that AB is equal to BA for all elements in our group. So that is a commutative property. But that is optional for a group. So something is a group without having to have the commutative property. But if it does have the commutative property, then the group is called abelian. All right, so that is the definition of a group. And in the next video, we're going to look at a bunch